Okay, picture this. You're getting dressed in the pitch black. If you have 10 black socks and 12 blue socks all mixed together in a drawer, how many do you have to blindly grab to guarantee, absolutely guarantee that you pull out a matching pair? Just, think about it for a second. The answer? Just 3. I know, right? Intuitively, it sounds kinda impossibly low considering how many socks are actually in that drawer. But here's the thing. To guarantee a pair from just 2 colors, picking 3 socks literally forces a match. Think about it. If your first 2 picks are 1 black and 1 blue, well, that third sock has absolutely no choice. It has to be one of those 2 colors. And boom, you've got yourself a pair. Okay, let's dive into this. Welcome to our explainer on a foundational and honestly beautifully elegant mathematical concept known as the Pigeonhole Principle. Our goal today is to demystify how this incredibly childlike observation, like picking socks out of a drawer in the dark, is actually the secret key to solving some of the most complex logic and computer science problems in the modern world.
Here's our roadmap for the explainer. We'll start with the deceptively simple principle, move on to the generalized form, tackle the strong form theorem, look at real-world applications, and finish up with some mind-bending solved problems. Section 1. The deceptively simple principle.
So the formal definition of the pigeonhole principle goes like this. If n items are put into m containers, and n is strictly greater than m, then at least one container must contain more than one item. Now that n greater than m part, that is the absolutely unbreakable mathematical foundation of this entire concept. You literally cannot defy it. Let's anchor this with a core metaphor. Say you have a flock of 13 pigeons, those are our n items, flying into 12 pigeonholes, our m containers. What happens? Well, since 13 is strictly greater than 12, at least one hole is going to get a little crowded with 2 or more pigeons. Bringing it back to our sock drawer puzzle, the 3 socks you pulled are your pigeons, and the 2 available colors are your pigeonholes. Because 3 is greater than 2, one color hole just has to accept at least 2 socks. It's that simple.
Section 2. The generalized form. Now, here is the generalized formula. It uses what mathematicians call a ceiling function. That just means you evaluate the math and then always round up to the next whole number. So the formula states that if n items are placed into k containers, at least one container has the ceiling of n divided by k items. Let's look at a real-world example. If you have 100 students, our pigeons, and you sort them by their birth month, the 12 pigeonholes, you simply divide 100 by 12. That gives you roughly 8.33. Apply that ceiling function to round up, and you mathematically guarantee that at least 9 of those students share a birth month.
Now, what's really interesting about this is how we can apply this generalized form to a slightly harder problem. Imagine a marble bag containing exactly 10 red, 10 white, and 10 blue. What is the absolute minimum number of random picks you have to make to ensure you get 4 of the exact same color?
The answer is exactly 10 picks. To understand why, you kind of have to imagine the absolute worst-case scenario for your goal. You want 4 of one color, right? But you keep drawing perfectly evenly. You draw 3 red, then 3 white, then 3 blue. So you've made 9 picks in total, and you still don't have 4 of any color. But at this point, your pigeonholes are completely full. Your 10th pick, no matter what it is, has to be red, white, or blue. Whichever one you pull becomes the inevitable 4th matching marble.
Section 3. The strong form theorem.
Okay, the strong form theorem gives us this formula. Q1 plus Q2 all the way to Qn minus n plus 1. Now don't let the variables intimidate you. This is absolutely perfect for complex problems that involve different specific quotas. For example, say you're forming a student club and you need either 10 freshmen, 8 sophomores, 6 juniors, or 4 seniors. You simply plug those specific quotas into the Q variables, subtract the total number of categories, which is n, or 4 in this case, and then just add 1. Doing this guarantees you draw enough random students to form the club.
But here is a brilliant little trap. Let's look at a scenario where a blind, unthinking application of that formula will give you the completely wrong answer. Consider a box filled with 6 red, 8 green, 10 blue, 12 yellow, and 15 white balls. What is the minimum number of random picks required to guarantee you get 9 balls of the same color?
Let's walk through it. Step 1, identify our variables. But wait, look at step 2. There are only 6 red and 8 green balls. They can literally never physically satisfy our goal of 9. If we plug them into the formula, the math just breaks. So step 3, isolate the valid colors, which are blue, yellow, and white. Applying the formula only to these gives us 25. Finally, assuming the worst-case luck again, we add the 14 impossible red and green balls back to our total.
So the crucial point is, your final answer is 39. You must pick exactly 39 balls to mathematically guarantee you pull 9 of a valid color. By recognizing which pigeonholes are impossible to fill and accounting for that junk data, the math remains totally bulletproof.
Section 4. Real-world applications.
This seemingly simple principle is actually a load-bearing pillar across 4 major disciplines. In coding theory, it's absolutely essential for understanding error detection, because encoding more messages than available unique code words guarantees some overlap. In graph theory and number theory, it proves complex properties about networks and integer sets. But I really want to focus heavily on how computer science absolutely relies on this to handle what are known as data collisions in hashing algorithms.
And this brilliantly illustrates that specific dynamic. In computer programming, think of your incoming data items, or keys, as your pigeons. The hash values, or memory buckets, are your pigeonholes. If a system is ingesting more data keys than it has unique buckets for, a data collision is mathematically unavoidable. Software engineers don't just sit around and hope this won't happen. They use the pigeonhole principle to know exactly when it will happen, allowing them to build robust strategies to handle those exact data collisions before a system completely crashes.
Section 5. Mind-bending solved problems.
Take this one, for instance. It is a mathematical fact that in any closed group of 1,001 people, at least 2 individuals have the exact same number of friends within that group. Now, how do we know this for sure? Well, any single person can have anywhere from 0 to 1,000 friends, right? However, it is logically impossible for someone in the group to have 0 friends, meaning they know absolutely nobody, while someone else has 1,000 friends, meaning they know absolutely everybody. Those 2 realities literally cannot exist at the same time in a closed group. Therefore, the maximum number of actual friend counts, our pigeonholes, is 1,000. So with 1,001 people, at least 2 match, guaranteed.
Let's ask an even bigger question and apply the principle at a massive scale. In a large city of 500,000 people, is it a guarantee that at least 2 people walking around have the exact same number of hairs on their head?
The answer is a resounding yes. Biologically speaking, the absolute maximum number of hairs on a human head is roughly $150,000. So we have 150,001 possible hair counts, starting from a totally bald 0 all the way up to 150,000. Those are our pigeonholes. Since the 500,000 people in the city wildly outnumber the 150,001 hair count pigeonholes, it is a mathematical guarantee that multiple people share the exact same strand count. You don't have to count a single hair to know for sure that it's true.
This principle builds a completely new way of looking at the world. The truly deceptive power of n simply being greater than m is that it takes a child's observation about a sock drawer and scales it up to prove vast, seemingly impossible truths about populations, digital networks, and infinite data. It shows us that absolute certainty is sometimes hiding right in plain sight. So, armed with the Pigeonhole principle, what impossible problem will you prove next?